So welcome back. We're ready to get started. It's my pleasure to welcome a first-time presenter, Professor Alex Lippert from SMU, right? Southern Methodist University. He's with the Department of Chemistry there. According to his students, Professor Lippert is one of SMU's best professors and makes organic chemistry clear if you come to class. So let's learn about a new volumetric display that he's developing. Thank you.
Okay, good morning, everyone. Thank you all for coming. I want to thank Greg Favalora for the invitation and the nice introduction. This has been fantastic. The 3D theater last night really was one of the most amazing things I've seen in a while. So this talk, I'm going to discuss a new type of volumetric display that we've invented using photoactivatable dyes. And so in the background, I have the holodeck, which to me is sort of the idealized picture of a volumetric 3D display where you really fill a volume of space with 3D objects. Now, the first thing to know about me is that I am, at heart, a synthetic organic chemist. And in particular, we specialize in the chemistry of light. And we do this a lot of times for biomedical imaging. So we can design small organic molecules that start off non-fluorescent, but then when they react with an analyte, they switch on fluorescence. At the whole animal level, we do something similar, but with chemiluminescence. This is a glow stick chemistry. We've also used this chemiluminescence to do some in vitro assays to monitor both analytes in humans. And so in the course of doing this type of biomedical imaging, we come across these really fantastic images. This is a super resolution image of a neuron, and it's a 3D data set, but whenever I see this presented, it's always on a 2D display where you lose that 3D information unless you do these tricks like using linear perspective to see the 3D data set. But of course, linear perspective was invented in the Renaissance times. This is pretty old technology. Now, the holodeck is sort of the idealized version of a volumetric 3D display, but a more accessible version might be what you would see in Star Wars. And I think if we could have even a display that would be more accessible like this, it would really change a lot of aspects of our life. Communication, if you could communicate with a hologram with someone in real time, I think that would change our interactions. Of course, there would be defense applications. I'd really like to see a volumetric 3D TV or gaming system where you could really sit around a table and play a game on a volumetric display. And then also for biomedical imaging, a little bit closer to home, if you could actually display biomedical imaging data in 3D, I think this would help radiologists better identify abnormalities, help guide surgeries, as well as help to communicate with patients. And so, of course, there has been some work on volumetric 3D displays. Some of the earliest examples that I found use these rapidly rotating screens, and you scan a beam so it hits it at a certain point in its rotation, and your eye puts it together as a 3D image. More modern manifestations of this use a high-speed DLP projector, and we've seen this in a couple talks already, and for us at least, this is a well-characterized benchmark that we aspire to. There's also static volume displays, there's active display units, but as chemists, we were really attracted to this type of display that uses 2-photon upconversion to generate 3D images. So what this consists of is a glass doped with lanthanide metals, and what you can do with this is you can use 2 different wavelengths of laser beams at high power, and only where they cross will you get this 2-photon upconversion into an excited state and luminescence only at the crossing of those 2 beams. This is really neat, but these tend to be very expensive to fabricate. You need very high laser power, which can be expensive and also a safety issue. So we thought we could use some of the responsive chemistry to maybe get around this problem and use lower light powers. And so the idea was to use this type of molecule, a photoswitch. And these have actually been involved in 2 recent Nobel Prizes for chemistry in super resolution microscopy, as well as in the field of molecular machines. And so this molecule under normal circumstances closes up, it's non-fluorescent, doesn't absorb light. If, however, you irradiate it with ultraviolet light, it does a photochemical reaction that changes its structure and now makes it capable of absorbing and re-emitting light. And so if you then excite the fluorescence with a visible light beam, you get fluorescence emission only where the 2 light beams intersect. Importantly, this process is reversible, so if you turn off the UV beam, or if it diffuses off the path of the UV beam, it closes up and you don't see any light emission. So only where the two beams intersect do you get light emission, so you can control in 3D space where you generate an image. At least this was the idea. So we had a number of questions to answer before we knew this would work. First, what photoactivatable dyes would be suitable? I showed you one example of a photoactivatable dye, but there's many families of them. Would this emission be bright enough to observe with the naked eye? Importantly, could we get the photoswitch kinetics, the on rate and the off rate, to be suitable to get nice images? And ultimately, what type of resolution, contrast, images, and animations can be generated? So the students working on this project, the lead was actually an undergraduate researcher, Shreya Patel, who's now doing her PhD at UCLA. Jen Zhao is a senior graduate student in my lab that made large quantities of the photoswitch dye that we used. And I'll also show you some images done by Cecilia O'Brien, a high school student that worked in our lab over a summer. So at the outset, we went to the lab and we synthesized this molecule. It's pretty readily available. I would estimate about $1 per gram. And we confirmed the photoswitching properties. Before shining UV light, there's no absorption in the visible region. But after you're irradiating it with UV light, you get this new absorption peak centered at 565 nanometers. And so to see if this idea would work, we did sort of a preliminary experiment where we dissolved this molecule in a vial with dichloromethane and got two laser pointers, a green laser pointer, actually the same exact model as this laser pointer, and a 405 nanometer laser pointer, and just aiming them together, we could get sort of a point of enhanced fluorescence emission where they cross. If you kind of turn off the lights and take a picture of it, you can maybe see it a little bit better. And then if you turn off this 405 nanometer laser beam, you get rid of the blue background and you can see sort of a point. So this was a preliminary demonstration that we could actually at least make a voxel. So this was neat, but there's some problems, mainly the slow thermal fading. So this dot would fade away, but it was on the order of minutes to hours. More problematic is if you kept shining UV light on this solution, eventually you would get this pink solution that just never faded away. So we were scratching our heads for a while, but there was some literature precedent using these as acid-sensitive probes, so they become more fluorescent when there's acid around. So my student Jen had the idea, maybe we can add some base to it. Sure enough, if you add 1 drop of a triethylamine base, you instantaneously get a clear solution. So we analyzed this a little bit better, doing the same type of vial experiment, but this time with the presence of triethylamine. When you turn on the UV light, you see the red dot glowing at the intersection of the UV light beam and the green light beam. And now, with the presence of triethylamine, it turns off within seconds. Importantly, if you add more triethylamine, it turns off faster. With less triethylamine, it turns off slower. And so at this point, we had been able to make a sort of one voxel, but we wanted to make images, so we needed a way to pattern the light. So we turned to projectors. These pico projectors are actually pretty readily available now for a visible light source, and I actually just went to Best Buy and bought one for a couple $100. The UV projector was a little bit harder to find, but luckily Texas Instruments is down the street from SMU, and one of their clients sells this Pro 4500 UV projector, primarily for 3D printing applications, but it works pretty nicely for our purposes. And so with these in hand, we did our kind of first demonstration of a volumetric image, here using a Erlenmeyer flask that we use in the lab. What I'm showing you here are the PowerPoint slides. So right now we're using PowerPoint to generate these images. So from the visible projector, we project a green square. From the UV projector, we have a series of bars. Wherever the visible square intersects with the UV bar, we get a red square in the flask. We can also switch this pattern if we go from the square to a grid of bars. Now we can get this volumetric 3D image of a grid of bars. And so each point here is a sort of a point source of fluorescence emission. And so this was a really fun day. This was like late at night in my office after all the students had gone home. And it was at this point where I really got some other students working on the project. And so with Shreya, who had some mechanical engineering background, we designed what we call a 3D light pad, a 3D digital light photoactivatable dye display, where we got a custom-built quartz imaging chamber filled with a solution of our dye, the green and UV projectors, and we use various bandpass filters to get rid of some of this blue background light. So this is a photograph of the setup. So between the UV projector and the imaging chamber, we have a UV bandpass filter. Between the imaging chamber and the observer, we have a long pass filter, and we control everything with 2 PCs. And so we looked at various filters to get rid of some of this blue background light. At the top, we don't have any UV bandpass filter. At the bottom, we add a UV bandpass filter, and we reduce some of this blue light background. Then when we look at various long-pass filters, we find that the 550 nanometer long-pass filter sort of has the best contrast. So with that filter set, we did some preliminary characterization of the display. So one of the things we looked at was kind of the minimum observable voxel size. And we did this by projecting a square from the UV projector, square from the visible projector. At the intersection with large squares, you get sort of this large solid cube of fluorescence emission. And as we get smaller and smaller and smaller, we get down to about 0.68 millimeters cubed as the minimum dot that we can reliably see. We also looked at the resolution. Here we define it as the minimum space you need to see 2 different bars. And using that definition, we get down to about 200 micrometer resolution. And more qualitatively, we're almost at the resolution of the projector itself. A little bit of fuzziness, at least for sort of these sort of flat 2D images. So we tried to see what types of images and animations we could make. So the first thing we did was the SMU mascot, the Peruna. How we do this is we project a bar, which makes kind of a green plane of fluorescence activation, and then we do a UV pattern of the horse. So wherever the UV pattern intersects with the green light, we get a nice high-resolution image of Peruna, the SMU mascot. We can also do some shameless self-promotion. We can do our Lippert lab logo, and the benchmark here is that we can have easily readable text. We can also project the molecule itself, the N-phenylspirolectam-rhodamine photoswitch. And here we see that we have enough resolution to see the double bonds in the aromatic rings, as well as the atomic labels. And we can actually do photograph quality resolution. If we project a photograph of Albert Einstein from the UV projector, then this converts it to a grayscale of UV, and we can sort of clearly see that it's a picture of Albert Einstein. Now, Nature didn't want to publish this image because someone owns the copyrights to Albert Einstein, at least his image. So I did a selfie of myself during my time wandering in the desert between the time I was at Berkeley and in Dallas and SMU. So this is good, but so far these are really 2D images at a defined point in 3D space. So we can move this bar back and forth and kind of move where this plane is. But if you want real 3D images, you want to structure the light from both of the projectors. So we can do this. We can do a triangle from the UV projector and a triangle from the visible projector, and we get kind of a pyramid floating in the middle of the flask. Again, it's a volumetric image. You can look at it from different angles and get a different perspective. We can do something like a cube by doing a square from the UV projector and a square from the visible projector, and we get a cube of light floating in our chamber. We can kind of switch up the patterns and do something like a cylinder by doing a circle and a block. And we can actually show the stereochemistry of the molecules. So organic molecules are 3D objects. And so by using this technique, we can, and designing our patterns appropriately, we can show that this top ring is actually at 90 degrees from the bottom ring. So we can actually show the 3D structure of the molecule. We can do household objects like a chair or a table. So we can do a lot of things, but there are some limitations that I do want to sort of bring up. One problem that we have, I think is a common problem with beam addressable displays, are this problem with ghost voxels. So to explain this, if you want to excite a voxel, you need a UV light beam to cross with the visible light beam. You can excite a voxel, no problem. If you wanted to excite another one up here, you need another UV beam, another green beam. You can excite that, but you get these other points where the beams cross, and you get this unwanted excitation of ghost voxels. Now, there's some strategies to get around this, and I like to take this example of an active display unit from Duncan McFarlane, who recently moved to SMU a few years ago. And what this is where in the circles you have a scattering matrix, and the lines are a waveguide. And so what you can do is you can excite each voxel independently by virtue of this diagonal array. It comes at the cost of resolution because you have some dead space here, but it's a way to sort of get arbitrary image generation. 3 minutes. So we can do this using a continuous line, and we can change that pattern up. And if we really play with it, and the movie looks like it's running a little slow, but I did want to show this. This is what our high school student made during our summer here. And it does a good job of showing you the different perspectives you can get. We have a little bit of a larger bottle here, but you can design things. We can also do animations. If you just animate the green light, you get sort of perfect real-time animation because it just depends on the fluorescence excited state. If you start to move the UV light, you get sort of this trailer background image. We can tune this a little bit by adding more or less space, but this is something we want to overcome. If you just keep the UV light static and only animate the green light, you can get kind of true frame rate animation. This movie's running a little bit slowly, but this actually runs at the perfect without any delay. And Cecilia also did some of her animations, and again, she kind of pans around so you can get a good idea of what this is looking like. And here she has a horse running through the flask, and she also did one of these reverse images with the horse running around. So this is kind of where we are right now. Oh, she also did like a 3D Pong, which I think is going to be our project for next summer to really get like a 3D Pong game with this display. So I think we've shown that we can overcome these basic limitations and get a display where we can actually get good resolution and contrast. Going forward, the chemistry, we're working on making a red, green, blue photoactivatable dye set for true color. And we're also looking to do this in the solid state using optical polymers. And then there's a lot of engineering to do here, and we're really doing our best, but I'd be happy to sort of work with anyone that's interested in this project. So just to end the acknowledgements, I try to highlight the students as they went. We have funding from NIH and NSF. And I do need to disclose a financial stake in BioLume Sciences LLC, which is they're developing an asthma monitoring technology. Didn't talk about it here, but SMU still wants me to stamp my conflict of interest. And thank you all for your attention. This has been a fantastic conference, and I'd love to return in future years.